Hello there, this is Truth Socrates. Welcome to today's video where we will be studying the natural exponential function. So our goals for this video are to construct the natural exponential function, and that is going to come from our previous topic, which was the natural logarithm function. We will prove and apply the properties of this function, and we will prove and apply in particular the formulas for its derivative and antiderivative. Okay, so to begin, we will go to GeoGebra and we will take a look back at the natural logarithmic function, and we will see how to construct its inverse, the exponential function, from there. All right, so here we are, and we said last time that we have the natural logarithm function, ln of x, so there it is, and we saw that, well, there was really just one number that we knew in the beginning, and that was ln of 1 is 0. But we also saw the special number e, Euler's number, where e was that real number whose ln is 1. Okay, so if we draw the horizontal line y equals 1, the x-coordinate of that point of intersection, that is the number e. Okay, so of course GeoGebra knows what e is. It is approximately 2.7 to 128 and so on. So there is the point E1. So we can hide this line now. And of course we said that ln of 1 is 0. So 1, 0 is a point on the graph of the natural logarithm function. Okay, what else did we say in that last video? The derivative of ln of x is 1 over x, because ln of x came from the definite integral from 1 to x of 1 over t dt. And by the fundamental theorem, that is going to tell us that the derivative of ln is just 1 over x, not 1 over t, but 1 over x. But since x is allowed only to be a positive number, 1 over x is also positive. So therefore, as we can see with our own two eyes, ln of x is an increasing function from 0 to infinity. So it's going to be injective, 1 to 1. If you intersect any horizontal line with the graph, you will only get one point of intersection. And we saw that earlier with y equals 1. We got the special number e. Okay, we also said that as x goes to infinity, ln of x also goes to infinity, but very slowly. Okay. On the other hand, thanks to the three properties of logarithms, which we will bring up later on, as x approaches 0 from the right, ln of x goes to negative infinity. Okay, so yeah, we can drag this up here. Yeah, see how it is diving down, down. Okay, so that tells us that the range of the natural logarithm function is from minus infinity to positive infinity. Okay, we're now ready to put it all together. Our ln of x is injective, it's 1 to 1. Its domain is from 0 to infinity. Its range is from minus infinity to plus infinity. So the inverse function exists, and the domain will be from minus infinity to plus infinity, and the range will be from 0 to infinity. Okay? Now, we know exactly 2 points on ln of x, so we also know exactly 2 points on the inverse function. So we switch x and y, so instead of e1, we have 1e. Okay, so that is the twin point of e1. And instead of 1, 0, we have 0, 1. So that is the twin point of 1, 0. Okay, so what were our observations? Oh, we need a mirror. So we said that to get the graph of the inverse function, we reflect across y equals x. Okay, and you can turn your head this way, 45 degrees, or if you prefer, this way, 45 degrees. Okay, so this is our mirror. This point is reflected over here. This point is reflected over here. So what happens as ln of x approaches its vertical asymptote? Well, x and y exchange places, so this says as x goes to infinity, as x goes to 0 from the right, y goes to negative infinity. Okay, so we'll say that backwards. As x goes to minus infinity, y approaches 0 from the positive direction. Okay, so this portion of ln of x will reflect to this portion of our inverse function. Okay, so it's going to go this way. It's going to hit 1, 0. It's going to hit E1. And what about this? Well, as x goes to infinity, y goes to infinity also very slowly. So not much to reverse there. As x goes to infinity, y also goes to infinity. But this time, y goes to infinity faster. Okay, so without further ado, we will ask GeoGebra to sketch the graph. The name of the function for the inverse of ln of x, for now, will be called the exponential function of x. Okay, there you go, exp of x, or exponential of x, a little bit easier to pronounce. Okay, so yes, we can check this inverse function is a perfect reflection of our original function, ln of x. All right, we said a lot of things in the last 5 minutes or so, so let's summarize them. We observed that the natural logarithm is injective because it is monotonic increasing. The domain of ln of x is 0 to infinity, and the range is all real numbers. Okay, so because ln of x is injective, it has an inverse function, which we will call, for now, the exponential of x. And we switch the roles of x and y. Okay, so let's write y equals exponential of x. And the domain of this inverse function is all real numbers, which is the range of Lx. And its range is from 0 to infinity, which is the domain of L of x. Okay, so we have a meaning to an inverse function. X and y exchange roles. So y equals exponential of x means that x is the ln of y. Okay, where now x can mean any real number, but y has to be from 0 to infinity. Remember, we can only plug in a positive number into the natural logarithm function. Okay, the vertical asymptote for the ln function became a horizontal asymptote for the exponential function. And in particular, we saw that the limit as x approaches minus infinity of the exponential function is 0. But on the other hand, the limit as x approaches positive infinity of the exponential function is also positive infinity. Okay, we also saw 2 points in our original function. We said that ln of 1 is 0 and ln of e is 1. So, again, exchanging the roles of x and y, we can conclude that the exponential of 0 is 1 and that the exponential of 1 is e. So we also found 2 points in the graph of our inverse function, 0, 1, and 1e. And we are now going to do a little bit of calculus. All right, so our next job is to find the derivative of the exponential function. Okay, so let's give it a name. Y will be the exponential of x. And again, that means that x must be the natural logarithm of y. Okay, so we're going to do implicit differentiation. We're going to take the derivative of both sides of that equation. Okay, so let's write d by dx of x on one side must be the derivative of ln of y on the other side, also with respect to x. Okay, but the derivative of x is simply x, but we said that the derivative of ln of y is 1 over y. Okay, but again, don't forget the chain rule. Every time you take the derivative of something that involves y, you need the chain rule. So we multiply that by dy by dx. Okay, so let me borrow this. Okay, so there we go. We're looking for dy by dx. So therefore, we isolate it here on the right side, and we will bring the 1 over y over to the left. Okay, so there you go. Not 7, y. Okay, dy by dx must be y. Okay, but wait a minute. Who is y again? Y is the exponential function. Woohoo! So therefore, dy by dx, let's put it on the left side. It's more natural there. Must be y, which is the exponential function of x. Okay, so this is a little bit weird and might bother you for a little bit. We started out with the exponential function, and the derivative of that exponential function is again the same function, exponential of x. Okay, so we have, of course, never seen a function that behaves like this. Power rule, derivative of x cubed is 3x squared, not x cubed. Okay, the derivative of sine is cosine. Okay, fine. The derivative of cosine is minus sine. Okay, but it's not the same original function. Okay, so that is both good and maybe disturbing. Okay, the exponential function is, of course, very important in mathematics. And for those of you who are continuing on all the way to differential equations, it makes a very has a very important role in the study of differential equations. This equation tells us that the derivative of y prime equals y. Okay, so there you go. That is one of the simplest kinds of differential equations where you see y and y prime in the same equation. And now we know that the exponential function is the solution to this differential equation. Okay, so there's our derivative formula. But every time we have a derivative formula, for free, we get an antiderivative formula. So this says that the antiderivative of x, of the exponential function, x of x dx, is also the exponential function plus c. All right. Now we started off with the derivative for the exponential function because it gives us very useful information. It tells us about the monotonicity property of the exponential function. The derivative is the same function, exponential of x, but we said its range is 0 to infinity. Okay, in other words, it's positive. Okay, so when the derivative is positive, your function is monotonic increasing, and we saw that in GeoGebra. So that tells us something very important about the exponential function, and we will use that property in a little bit to talk some more about what happens to the exponential function when you plug in some very special numbers. All right, but to prepare ourselves for what we're going to do next, though, let's review the cancellation properties for a general situation where you have an injective function and its inverse. Okay, so suppose you have a function which is injective with domain A and range B, which could be intervals, and g of x is the inverse function. Okay, then we have the following cancellation properties. Okay, so for any A in the domain of f of x, g evaluated at f of a takes you back to a. Okay, and on the other hand, for all b's in the range of f of x, which is the domain of g of x, f evaluated at g of b takes you back to b. Okay, so now let's write this in terms of our pair of inverse functions. We have ln of x is the original function f of x, and the exponential function is our inverse function g of x. Okay, so the domain of ln of x is 0 to infinity. So our first statement says for all x from 0 to infinity, the exponential of ln of x is once again x. Okay, and the range of ln of x is all real numbers. So for all real numbers x, the ln of the exponential of x takes you back to x. Okay, so why am I not using a and b? Well, in calculus, we usually deal with the letters x. Okay, so instead of using x and y, now that would be really confusing, don't you think? Okay, so we use the same letter x in both of these equations, but we do qualify that in the first equation, x must be positive, and in the second, anything goes. X can be any real number. Okay, so when we developed the natural logarithm function, we saw that it had three properties. Okay, we'll bring back all three of them in a little bit, but let's focus on the third property, which is about powers. Okay, for any positive number a and for any rational number r, the ln of a to the power r is r times ln of a. Okay, so this only works for a rational number because we saw that the power rule for derivatives has been proven only for x to the power r, where r is a rational number. And we needed that in order to prove this property. Okay? But e, the special number e, is also a positive number. So we can apply this equation to a equals e. So we get ln of e to the r is r times ln of e. But we said, wait a minute, ln of e is exactly 1. Okay, so we get r times 1, which is of course r. Okay, but now let's think about the cancellation properties. If ln of e to the r is r, this means exactly the same thing as the exponential of r must be e to the r. Okay, ln of a equals b means that the exponential of b must be a. Okay, but wait a minute, now we have two things that represent ln of e to the r. Okay, so we have exponential of r is e to the r. Okay, what does that mean? Exponential of r must be e to the r. We can therefore say that the exponential function, when you plug in a rational number, must give you just e to the power r. Okay, so that is the conclusion that we get from the third property for logarithms and the cancellation properties for the natural logarithm. All right, that doesn't help though if our exponent, our r, our input number, is an irrational number. We don't know what it means to raise a number by an irrational number. Okay, we're going to see that in the next video when we talk about general exponential and logarithmic functions. Okay, so for now, let's think about square root of 2. Okay, we know that is an irrational number, but it is approximately 1.4142135 blah blah blah. Okay, so square root of 2 is between 1.41 and 1.42. Okay, when a decimal terminates, it doesn't go on forever. Okay, it ends with 0, 0, 0, 0, and so on. Now that's a rational number. Okay, you can think of that as 141 divided by 100. Okay, so where are we going with this? Well, we saw that the derivative of the exponential function is itself. So therefore, because it's a positive function, it must be increasing. Okay, and we saw it in the graph one more time. Okay, so therefore, the exponential of square root of 2 must be between e to the 1.41 and e to the 1.42. Okay, so we already know that the exponential of a rational number is just e to that rational number. Okay, so e to the 1.41 is smaller than the exponential of square root of 2. So let me borrow this. I guess I'm also bothering this. And it must be smaller than e to the 1.42. Okay, so these numbers, we know what these mean. Okay, because we know how to take rational power of any number. Okay, so, oh great maple, what is an approximation for this? It's about 4.137. Okay, so that is the upper number. The exponential of square root of 2 is smaller than 4.137. And who is this smaller number? You're about 4.09. So there you go. Whatever exponential square root of 2 is, it's bigger than 4.095, but smaller than 4.137. Okay, that's not a very big interval, is it? Okay. However, we have more digits here. Okay, so would you like to have a more accurate answer? Okay, so, whoops, let's bring back that number. 414, okay. So instead of just 1.41, let's do 42. Okay, so we will add 2 more digits. Let's copy this inequality. So we get 1.4142, and it's smaller than 1.4143. Okay, so see what I did there. I kept the first 4 decimal places, but the next digit after 2 is a 1, so therefore I can replace the 2 with a 3. That will be a bigger number. Okay, so let's play the same game. Let us plug in the bigger number and get its approximation. Oh, great Maple, you are approximately 41136. Okay, so let's just keep 4 decimal places. Okay, and how about the smaller number? 4142, you're approximately 41132. Okay, so we get a much smaller interval here. I don't know who x of square root of 2 is, but it's somewhere between 4.1132 and 4.1136. Okay, now GeoGebra gave us the complete graph of the exponential function, and of course Maple is also pretty clever. It gave us these approximations. So can Maple also tell us who is e to the square root of 2? Okay, I did e to the 1.4142 and 1.4143. Is Maple smart enough to give me a good approximation, or, what does this even mean? Okay, we don't know what it means for a number to be raised to an irrational number. But Maple is very clever. What do you say, Maple? Ooh, it's about 4.11325. Ooh, yeah, check it out. 325, 32, and this is 1136. Okay, so that is valid. I would say that's a convincing approximation for the exponential of 2. And in case you are doubting, well, wait a minute, why is that the same as exponential of 2? Can it tell us what that is? And, oops, my bad. That's exponential of 2. And we are looking for exponential of square root of 2. Wait a minute, I'm missing something. Okay, does Maple know that it's supposed to be the same thing? Yes, of course. Okay, it's exactly the same thing. All right, so now we have a better notation for the exponential function. We will just write it as e to the power x for any real number, even if that x is an irrational number. Okay, so we have translation for what it means for y equals e to the x. It means exactly the same thing as x must be the ln of y. We have 2 cancellation laws, and we have the old version, and now we have a new version. For any positive number x, we had x of ln of x must be x. We can now write this as e to the ln of x must be x. For all real numbers r, we had as our old version ln of x. See how clumsy that is? Must still be x. So this time, we can say that the ln of e to the x must also be x. Isn't that a lot more natural? No pun intended. All right, I said earlier that we're going to bring back the properties of logarithms, and here they are. for all positive numbers a and b and rational numbers r, ln of a times b must be ln of a plus ln of b. Ln of a divided by b must be ln of a minus ln of b. And ln of a to the power r must be r times ln of a. Okay, so this is the property that we used earlier when we said that exp of r is simply e to the r. Okay, and that prompted us to say, okay, instead of exp of x, which is hard to pronounce, we will just call it e to the x. Okay, so these three properties will translate to three properties for the exponential function. All right, I had a little bit of something missing at the bottom, so here it is. So let's summarize what we have so far above. We saw that the exponential function e to the x, it's continuous. We even got its derivative. It's differentiable with derivative e to the x as well. And the domain is all real numbers with the range from 0 to infinity. So another way to say that is that e to the x is positive for any real number. That says two things. E to the x always exists and always has to be positive. Okay, so we have three properties of logarithms, and they translate to these three properties for the exponential function. For any two real numbers u and v and rational number r, e to the u times e to the v must be e to the u plus v. E to the u divided by e to the v must be e to the u minus v. And e to the u raised to the power r must be e to the r times u. Okay? And you might say, okay, can we switch them backwards? It will be possible, but not today, not in this video. This will come in our next video. Okay, we also saw that the vertical asymptote of ln of x turned into a horizontal asymptote for e to the x exponential function. So the limit as x goes to minus infinity of e to the x must be 0, and the limit as x goes to positive infinity of e to the x must also be positive infinity. Okay, so as we go to the right, our e to the x keeps getting higher and higher and higher. Okay, so we are going to prove the first property. The other two will be left as exercises. Okay, we want to prove that e to the u times e to the v must be the same as e to the u plus v. Okay, so the idea is to give names to these two symbols. So e to the u, we will call it a, and e to the v, we are going to call it b. Okay, so what are we trying to show here now? We must show that a times b, where's my times? A times b, which is e to the u times e to the v, must be the same as e to the u plus v. Okay. However, what do we know about these symbols? Okay, so e to the u equals a means the same thing, that ln of a must be u. Okay, outside please, equals u. There you are. Okay, and what about the other equation? E to the v must be b means that the ln of b must be v. Okay, so now what do we have on the other side? Ooh, we have e to the u plus v. Oh, wait a minute, we know u and we know v, so we can add those together. Okay, so thus u plus v must be ln of a plus ln of b. Ooh, does that sound familiar? Let's go back to our properties here. We said that, oh, ln of a plus ln of b must be ln of a times b. Excellent. So we know that ln of a plus ln of b must be the same as ln of a times b. Okay, so we already have this over here. Okay, oh, wait a minute. So now let's think about cancellation, and what does it mean for ln of something to be equal to something? Okay, so this we can rewrite directly as u plus v must be the ln of a times b. Okay, but we can write this in exponential form. This means that e to the u plus v must be equal to a times b. Okay, but wait a minute. We said that a times b is the same as e to u times e to the v. Yay, there you go. So e to the u plus v is exactly the same as e to the u times e to the v. Okay, so we're going to end this video by applying the derivative and antiderivative formulas. Let's start by, well, we have a better notation for the exponential function now. We're just calling it e to the x. So our derivative formula can be written as the derivative of e to the x is just the same as e to the x. Okay, so you have until tomorrow to memorize this formula. Just kidding, you already know it. Okay, so we have two transformed functions here. Instead of e to the x, we're looking at e to the 3x and e to the minus 4x. Okay, so what are the derivatives of these two transformed functions? Okay, so the derivative formula can be applied here, except the 3x tells us we need the chain rule. Okay, so the derivative of e to the 3x is still e to the 3x, but we have to multiply that by, whoops, not divide, this one. We have to multiply that by the derivative of what is in the exponent, which, if you recall, that was what was inside the exponential function. So e to the 3x is really exp of 3x. Okay, so we have to apply the chain rule to 3x, and of course that simply is 3. And 3 looks better in front instead of on the right. Okay, so there we go. The derivative of e to the 3x is 3 e to the 3x. Okay, what about e to the minus 4x? Okay, let's do this a little bit faster. It is still e to the minus 4x, but chain rule, we need to get the derivative of negative 4x, and it goes in front. Okay, so it's minus 4 e to the minus 4x. Okay, so I want you to notice something. Okay, we said that the range of the exponential function is all positive numbers. Okay, so e to the 3x will always be positive, but we're multiplying by a positive number 3 in the first example, so this is always positive. Okay, so we mentioned earlier the first derivative tells us that a function is increasing or decreasing based on its sign. Okay, when the derivative is positive, our function e to the 3x is increasing. Okay, on the other hand, the derivative of e to the minus 4x is negative 4 times e to the minus 4x. Don't let that negative exponent, negative 4 in the exponent, fool you. E to the minus 4x is still positive because e to any number is still positive. So we're multiplying a positive number by a negative number. So this time the product is negative. Okay, so what does that mean? Our function e to the minus 4x is decreasing. So if let's think about the generalization. If the coefficient of x in the exponential function is positive, then our function is still increasing, just like e to the x. But if the coefficient is negative, then our function is this time going to be decreasing. Okay, so let's go back to GeoGebra and check our conclusions. All right, so we're back in GeoGebra, but we have a new, fresh copy. So this time, let us ask GeoGebra to graph as e to the x and not x of x. Okay, so of course this is the same graph that we saw last time. Okay, and if you don't believe me, let's also type in x of x. Yeah, they're exactly the same. Okay, so we said that our first example was e to the 3x. And so there you go. It is again an increasing function, but something interesting happens. Okay, let me flash it a little bit. Okay, so e to the 3x is lower than e to the x when x is negative, but it is higher than e to the x when x is positive. Okay, but again, both of them are increasing functions. Okay, so let's take a look at the other example, e to the negative 4x. And this time, ooh, check it out. It's going decreasing this time. Okay, and here's another way to think about it. Okay, we know in basic algebra that if you have a function where you plug in negative x instead of x, that has the effect of reflecting the graph of the function across the y-axis. Okay, so in particular, if we just do e to the minus x, there you go. So the graph of e to the minus x is a mirror image of the graph of e to the x. All right, so with that, let's do some integration. Okay, let's end with something simple. Let's find the antiderivative for e to the 3x dx. Okay, so of course the integration formula is integral of e to the u du is e to the u plus c. Okay, so it's pretty obvious that the u in this case should be 3x, what appears in our exponent, in our e to the x. Okay, so du is 3 dx, and dx must be 1/3 of du. Okay, I feel like we've done this a dozen times already. Okay, so now we can rewrite our problem. This must be the same as, instead of e to the 3x, we have e to the u, and our dx is 1/3 du. Okay, so we erase that. And of course, we can take the 1/3 out. 1/3 of e to the u du. And we can apply now our antiderivative formula. So we keep the 1/3, and we have e to the u plus c. Did I really need the parenthesis? Maybe not. Okay, so we can bring back, who is u again? U is 3x and plus c. Okay, there you go. That's not a very difficult integral. Okay, so if you're only integrating e to the kx, where k is a non-zero number, notice in general that you get k in the denominator here. So you get 1/k e to the kx as well. All right, so that is our video for today. In our next video, we are going to generalize what we just learned in the last two videos to construct exponential functions to any positive base and the corresponding logarithmic functions. All right, so until then, I will see you next time, and I hope you enjoy the rest of your day. Bye now.